Hi y'all, welcome back to chapter 14. In this part 3 on aldehydes and ketones, we are going to be focusing on chemical reactions or the chemical reactions that these molecules can undergo. So our learning outcomes for this section are to be able to predict and draw the structures for the reactants and products in the oxidation or reduction of aldehydes or ketones, and to predict and draw the products of the addition of alcohols to the carbonyl groups of aldehydes and ketones. So first off, let's talk about oxidation. So we've already sort of discussed this a little bit in our alcohols chapter, because if you remember, primary alcohols are able to oxidize to create aldehydes and then further oxidize to create carboxylic acids. So we're already sort of familiar with this. And then the same thing, right? Secondary alcohols may become ketones. So if you recall from the alcohol chapter, aldehydes, right, which is the first product of the oxidation of alcohols, right, of a primary alcohol, when we get an aldehyde, there is still a hydrogen here on this terminal carbon. So it can further undergo oxidation in order to form a carboxylic acid, such as ethanoic acid. Ketones, however, if you remember, do not have another hydrogen here on this carbon to lose. Therefore, it will not undergo any further oxidation. So when we're talking about aldehydes and ketones, all we have to remember is that aldehydes will get converted to ethanoic acid in a further oxidation step, where ketones will not react in oxidation reactions. Now, a really nice test that chemists can do in order to determine whether we are working with an aldehyde or a ketone is the Toland's reagent test. So this utilizes a reagent which is comprised of a solution of silver as silver nitrate and ammonia. And it is going to oxidize aldehydes, but again, remember, ketones cannot oxidize. When this happens, the oxidized aldehyde then in turn reduces silver, and that's going to end up creating a layer on a surface called the silver mirror on the side of the container. So if this test tube contains an aldehyde, it will react with Toland's reagent to sort of paint the surface of this test tube silver, right? Which is sort of the same way that we are able to deposition silver onto a flat surface in order to get a mirrored surface. So we can actually do this in lab if you like, using Christmas ornaments or other things. It's a really cool reaction. But again, if what's in the test tube is a ketone, then you won't get this deposition of silver onto the surface, right? The silver will not become reduced in a solid. It will stay in solution, and there would be no reaction. All right, so let's do a quick learning check. Are you able to write the condensed structural formula and the name of the oxidized product when each of the following is mixed with Toland's reagent? So remember, Toland's reagent is going to act as an oxidizing agent on aldehydes to create an oxidized aldehyde that is a carboxylic acid. So we're taking this hydrogen off and we're going to replace it with an alcohol group. All right, and then remember, if this is a ketone, right, instead of a hydrogen here, we have another C or alkane chain, another carbon or alkane chain, then there will be no reaction, okay? So there'd be no product here. All right, so let's take a look. So butanal, right, here is butanal. First step is you want to recognize, is this an aldehyde or a ketone? So if you look at it, right, our C double bond O is at a terminal carbon, so that makes it an aldehyde, and it should react. What about acetaldehyde? So yeah, again, acetaldehyde, we see that that carbonyl carbon is at the end of the chain, and so it should react with Toland's reagent to make a carboxylic acid. And then what about ethyl methyl ketone? Well, if we look, we have ethyl, methyl, and then that ketone in the carbon. that we recognize that C double bond O is in the middle of a chain. There is no hydrogen here. So because it's a ketone, we should not get a reaction. All right. So when we're thinking about predicting our products, all we have to think about is A and B. And remember, our product of the oxidation reaction of aldehydes is that we replace these hydrogens with an alcohol group or an OH. So it's going to look exactly the same, but the hydrogens are a hydroxyl. And then when we name it, we'll learn about when we name carboxylic acids, but instead of butanol, it would be butanoic acid. And instead of acetaldehyde, it would be acetal acid. We'll look at that one. Ethanoic acid. That's what it's going to be. So butanoic acid and ethanoic acid, right? So again, all we're doing is replacing that terminal hydrogen with a hydroxyl in order to get our final product with Toland's reagent. Again, because the ketone in part C will not react, you would write no reaction there as the product. All right, so your turn. Log back into Mastering Chemistry and answer question 6 for me. Pause here, and then when you're ready, come back. All right, so the reverse of oxidation is reduction. So remember, with oxidation, we are increasing the number of bonds between carbon and oxygen and decreasing the number of hydrogens on that carbon. Here in reduction, we're doing the reverse. So we're going to be removing carbon-oxygen bonds, right? Decreasing the number of carbon-oxygen bonds and increasing the number of hydrogens to that carbon. So often these reactions are done under the presence of dihydrogen gas or sodium borohydride in a catalyst such as nickel, platinum, or palladium, right? So this is what you would see over the reaction arrow. And again, what we're going to see is a decrease in the number of carbon-oxygen bonds and an increase in the number of carbon-hydrogen bonds. So aldehydes are going to be reduced to primary alcohols, and ketones will be reduced to secondary alcohols. So again, this is the exact reverse of what we saw in our alcohol chapter. So if we look at propanol, right, which is an aldehyde, the C double bond O is at the end of the chain. When we add dihydrogen gas over a platinum catalyst, we are going to break one of the double bonds between carbon and oxygen, and we are going to put a hydrogen on that oxygen to give us the alcohol and a hydrogen on that carbon that is bound to the oxygen. So the two hydrogens on dihydrogen end up splitting and binding to the alcohol. And again, our product of any aldehyde reduction is going to be a primary alcohol. With a ketone, again, we're going to do the same thing. We're going to reduce the carbon-oxygen bond. So we're going to go from 2 to 1 bonds. And we're going to put hydrogens from that dihydrogen gas, one on the oxygen atom, one on the carbon atom. And again, when we are reducing a ketone, we will end up with a secondary alcohol. All right, so putting this into practice, let's predict the products for each of the following reactions. So again, the first thing you want to ask yourself, is it an aldehyde or a ketone? If it's an aldehyde, we're going to get a primary alcohol where we will reduce the number of carbon-oxygen bonds from 2 to 1, and we'll put a hydrogen on this oxygen and a hydrogen on this carbon to give us the primary alcohol. For the ketone, again, we are going to reduce the number of oxygen-carbon bonds. We'll put a hydrogen on that oxygen and a hydrogen on that carbon to give us the secondary alcohol. So we can look at that here, right? So here's our aldehyde. It's going to react with dihydrogen over a platinum catalyst to give us the primary alcohol product. Nothing else changes here. And we don't also, one other thing is we don't have to really worry about stereochemistry here, right? Because all we are doing is reducing that C double bond O. So again, aldehydes are going to be reduced to primary alcohols. Our ketone here is going to be reduced to a secondary alcohol. as the oxygen-carbon double bond is reduced to a single bond. And then we are going to put a hydrogen on this oxygen, and then what you don't see but is there is that other hydrogen is added to this carbon as well. All right, so ketones are going to be reduced to secondary alcohols. All right, so why don't you guys then go back to Mastering Chemistry on Chapter 7 and practice this skill. Pause here, and when you're ready, come back. Okay, so let's talk about hemiacetals and acetyls. So sometimes when one alcohol is added to an aldehyde or ketone in the presence of an acid catalyst, we are going to get something called a hemiacetal. A hemiacetal contains two functional groups on the same carbon atom. We have a hydroxyl, or our alcohol group, and we have what's called an OR group, right? Where there's usually like an additional alkane chain or something else here coming off of this oxygen. Hemiacetals are generally unstable and will react with a second molecule of the alcohol to form what is now a stable acetal and a molecule of water. So now the acetal, right, what was an alcohol and a CO with an alkane chain, now becomes two alkane chains coming off of the oxygens that are bound to that same carbon atom. And again, this is going to be much more stable. All right, so let's look at this in a little bit bigger picture. So let's say we have the molecule ethanol, right? So recognize that this is an aldehyde. So aldehydes will react with alcohols such as methanol to produce the hemiacetal. So let's look at what's happening here. What's happening here is that we are going to first reduce the aldehyde group, the C double bond O, to just a C single bond oxygen. The hydrogen from the alcohol is then going to bind to what was that aldehyde oxygen to give us an alcohol group here, right? So this CO is this original aldehyde C double bond O. Okay, so we've reduced this carbon-oxygen bond here. However, this now free unprotonated alcohol is then going to also react with this carbon in order to give us the hemiacetal. So just to kind of give you some perspective of what's happening here, when we reduce aldehydes using dihydrogen, notice that the dihydrogen molecule splits up into two hydrogens. One hydrogen goes to the oxygen, one hydrogen goes to the carbon. When we're doing this in the presence of an alcohol, instead, the one hydrogen or the hydrogen of the alcohol is going to end up on what was the carbonyl oxygen, and the remaining molecule from the alcohol, right, that alcohol or that oxygen and that methyl group or whatever the alkane chain is then going to add to the carbon like the second hydrogen did in the reduction reaction. Okay? Now, this hemiacetal is not stable, right? It's not going to exist long in the hemiacetal formation. And if there is excess methanol, then a second molecule of methanol is going to react to displace the hydroxyl group on the hemiacetal, adding to that carbon, and we end up with an acetal. So to summarize this, what's going to happen is an aldehyde and an alcohol will react in two steps to form the acetal, where whatever the alcohol is will bind to what was the carbonyl carbon, okay? And then you will also end up with a byproduct of water, right? Where this oxygen was the aldehyde oxygen from our aldehyde, and then the hydrogens are the two hydrogens that were coming off of the two molecules of alcohol that were needed to make the acetyl. Now, aldehydes are often more reactive than ketones because the carbonyl carbon is going to end up being a little more positive on the end of the alkane chain than if it's in the middle of the alkane chain. However, ketones can still do this reaction, right? So the presence of the two alkyl groups in the ketones also makes it a little more difficult, a little more sterically hindered for an alcohol to form a bond with the carbon in the carbonyl. So while this reaction does happen with ketones, it happens a little more often with aldehydes. It's a little easier. All right, so again, for example, this was our ethanol and methanol reaction, and we ended up with an acetyl group in which here was your original ethanol, and then here are your two methanol molecules that are attached to the carbon from the aldehyde. If we look at ketones, such as propanone, and we want to add ethanol to make an acetyl, here we can see our hemiacetyl where we add our first alcohol to that ketone carbon, and then our second alcohol to that, what was a ketone carbon, okay? And then you still get water. Now, this can also happen in cyclic compounds, and it's actually really important in cyclic compounds when we start studying carbohydrates, right? So one very important type of hemiacetyl is a cyclic hemiacetyl when we have both an aldehyde or a ketone, right, some sort of carbonyl group on a chain, and a hydroxyl group. So when we have a hydroxyl group and a carbonyl on the same molecule, that alcohol can then come in and attack the carbonyl carbon to form what is called a cyclic hemiacetyl. So a great physiological example of this is the molecule glucose. So the open chain structure of glucose looks like this. So glucose is an aldehyde, right? You'll see that carbon 1 has that C double bond O, but on each other carbon in the chain, we also have hydroxyls, right? These are all alcohol groups. Any one of these alcohol groups could come back and attack this carbonyl carbon in order to form our cyclic hemiacetyl of glucose. However, most likely it's this carbon 5 that just seems to be the most sterically stable version versus carbon 6 or carbon 4. You're not going to get anything smaller than 4, but you do, every now and then we can get a 4 carbon ring structure, and we'll talk about that when we talk about carbohydrates in our next lecture. However, the most likely scenario, and this isn't something you would know, right? This is something I have to tell you, but the most likely scenario is that the alcohol from carbon 5 folds back onto itself and reacts with the carbonyl carbon on carbon 1 in order to form that cyclic hemiacetyl. Okay? Now, an alcohol then can also add to this cyclic hemiacetyl to form the cyclic acetyl. And so this is the reaction that helps create the polymers of sugars that we have in our bodies. When we think about starch or glycogen, what's going to happen here is that a second sugar molecule, a second molecule maybe of glucose, can then come in, one of those hydroxyls on the glucose molecule then reacts with the carbon here, that hemiacetyl carbon, in order to lose or replace this alcohol with another molecule of glucose or some other sugar. Okay, so this CH3 here, right, we're talking about methanol, but this alcohol could be any other alcohol. And again, this is how we go from monosaccharides to disaccharides and then even longer chains, right? Because if this is another molecule of glucose, it too will have another hemiacetylcarbon that we can attach to over and over again. So if we look at that, for example, maltose is a disaccharide of 2 glucose molecules where you have an acetyl bond here shown in red. So this was that hemiacetylcarbon that another alcohol group on this sugar came in and attacked, and we created an acetyl linkage, right, or a disaccharide bond, okay? Now, because this is also a glucose molecule here, we see that we have another hemiacetylcarbon here, and you can see that by looking at the pattern of O carbon hydroxyl. This hemiacetylcarbon here could also react with another molecule of glucose to continue extending the chain. When we just have 2 glucose molecules bound in this way, it's called maltose. All right, so let's practice first identifying whether a molecule is an acetyl or a hemiacetyl. So the trick here is, again, to look at the carbon that has the 2 oxygens bound to it. If one of those oxygens is an alcohol oxygen or an OH, and one of those oxygens has a chain coming off of it or additional carbons coming off of it instead of a hydrogen, then it is considered a hemiacetyl, right? This hydroxyl group here is still open to react with another alkane chain or an alcohol with an alkane chain, okay? So A, we would consider as a hemiacetyl. B, however, if you notice, this carbon has 2 oxygens bound to it, right? But both of these oxygens have an alkane chain substituent on them instead of a hydrogen. Therefore, this is what's considered an acetyl molecule, right? So again, a hemiacetyl because we have a hydroxyl and an oxygen with an alkane chain. Acetyl because we have the 2 oxygens both with alkane chains. All right, so your turn. Let's log in to Mastering Chemistry and complete question 8. Pause, and when you're ready, come back. All right, so now let's practice predicting structures for the acetyl formed by adding methanol to butanol. Right, so the first thing you would want to do is draw your structure of butanol. Right, so butanol has 4 carbons, 1, 2, 3, 4, and we should have a C double bond O and a hydrogen. So we know that the C double bond O and hydrogen, that carbonyl group is at the end because it's butanol, right? We're talking about an aldehyde, not a ketone. It's not butanone, okay? So that C double bond O is here. The overall product, even though this happens in 2 steps, right? Remember, the hemiacetyl is not going to be stable. So the overall product is that we will simply draw that terminal carbon. Instead of a C double bond O with an H coming off this carbon, we will have a COCH3 coming up, and then a COCH3 coming down, and then that hydrogen remains, right? So this would be our full acetyl of this molecule. Note that I'm not asking you to name it here. I'm just asking you to draw the product. All right, so why don't you practice this with question 9. Pause, and when you're ready, come back. Okay, so just to summarize what we have talked about, aldehydes and ketones are a group of molecules in which we have a carbon-oxygen double bond. If that carbon-oxygen double bond is at the end of the chain, we call it an aldehyde. If it's in the middle of the chain, we call it a ketone. Aldehydes will test positive with Toland's reagent, as well as another test called Benedict's test, which we haven't talked about. That has to do with sugars, and we will talk about that in the carbohydrate chapter. Aldehydes will also react to form primary alcohols or carboxylic acids. They will also react to form hemiacetyls and ultimately acetyls. Remember, the hemiacetal is going to be unstable, so it's going to react with the second alcohol in order to form the acetyl group. Okay? Ketones, right, will reduce to make secondary alcohols, and then they will also react with alcohols to form hemiacetals and acetyls. Okay? So again, what's similar about aldehydes and ketones, they will both create acetyls, but what's different is when we reduce an aldehyde, we will make a primary alcohol and then eventually a carboxylic acid if we do a second reduction, whereas ketones will only react to form secondary alcohols, right? So yeah, aldehydes can be reduced to form a primary alcohol or oxidized to form a carboxylic acid. Remember, ketones can no longer be oxidized. All right. If you have any questions about this, write them down and email me, or bring them with you to our Zoom session that I will schedule for us probably next Friday. I think I'll be back in town in time to have a Zoom session with you guys on Friday. And if I have time, we can do one Sunday before our test as well. We can also spend time in class Monday in lecture before our test to go over any questions you have for our test that afternoon. All right. I hope you all have a wonderful day and keep on studying.